X8 Work-Kinetic-Energy Theorem. Explain what power is. Power is work per unit time. And power, this P, is not a linear momentum. If I multiply dt, both sides, this is a kind of changing variable. So this is this. Okay. Amount of work is a power multiplied by time difference. If this power is constant during a very tiny time interval. So this is the work. Okay, and what is work? Work is force times displacement, infinitesimal displacement. By the way, this is if I attach this notation, then we just sum all of the tiny pieces of the work. So this is the integral of work. In here, f dot dx, the vector scalar product, this the integration over displacement. We usually make change a variable, change the integral variable from the displacement to something else. Let's see. We remember force is the time derivative of linear momentum. That is mass times velocity. Okay. Why don't we substitute this here? This is force. We originally have the integral expressed as an integral over x. By the way, why don't we shift this guide in here? Then the integral variable has been changed to something else, not through x, but through velocity. Why? dmx dot scalar product dx over dt. What's that? This is the velocity. Haha, so this integral becomes force times the displacement is differential of mv scalar product v. That is x dot. Okay? We can pull this mass out. There's x dot dot dx dot. We are very familiar with this structure. You remember Leibniz rule applied to the scalar product, especially the same thing, a squared. Differential of a squared, that is a dot a, scalar product between the same vectors, and you will find the 2 times a dot dA. So this must be a differential of something else, that is this. Differential of 1/2 velocity squared is nothing but this. As a result, in the beginning, we had an integral over x. In the middle, we have integral over x dot, that is velocity, and we make another change of variable. We make an integral over a scalar that is, if I multiply m, what's that? This is, we define this object to be kinetic energy. Therefore, any integral is just nothing but itself. This identity operation. The dx integral is trivial x. So d kinetic energy, we call not a temperature, not a period, capital T is 1/2 mv squared. This integral is just a change in the kinetic energy when we define this 1/2 mv squared. This is called Coriolis work-kinetic energy theorem. Let us consider the at-root machine. That is, let us also consider the pulley, that is massless pulley and without friction for simplicity. We have two massive particles that are connected through a string. And again, if it is massless, it does not contribute to any motion, this pulley. In that case, pulley does changes does change the direction of tension. And the magnitude of tension at both the ends of a pulley must be identical to each other. Only if it has some inertia, the rotational inertia, it does contribute to the system and the tension can vary. But today, we do not consider the action of the pulley, so the tension, magnitude of the two tensions must be the same. And because the string is unstretchable, the amount of height, we assume that capital M is greater than small m. The system rotates counterclockwise. If it goes down with the magnitude of the length x, then this small m goes up with the same length. So it is going up, going down. Their magnitude of change should be the same, and it is increasing, and this is decreasing. Okay, we are all set. Because the string is not stretchable, sum of x and y, that is the length, constant. If I take the derivative, velocity sum must cancel. We don't denote the tension of the string by tan T. I told you many times, tension, if you write tension, this tension is always a positive definite. And depending on the situation, if you consider the motion on this object, the tension is going up. And if you want to describe the motion of this object, tension is opposite. You know, string. If you press the string, it cannot apply any force. String can apply to the system the tensile force. Tensile force is this kind of force, and this is compression force, and tension does not contribute this compression force. Instead, it can apply the tensile force. That is called the adjective of the tension. Okay. Equation of motion for capital M. We have this net force on this object is mass times acceleration, and then unit vector, that's fine. Along the unit vector, we have a gravitational force that is mg, that is mge1. In this case, this is going down parallel to the gravitational acceleration. And then this tension is opposite to the gravitational force. So that's the reason why I put the negative sign on it. Be careful. And then next we consider equation of motion for small m. Tension is going up and small m, gravitational force, again, the opposite direction. And this is a y double dot. However, so right-hand side, the same shape. However, we began with x plus y constant. So x dot plus y dot equals 0. And sure, double dot is also 0. Because of this relation, x double dot and y double dot are additive inverse. So I need to put the negative sign on it when I replace y with x. That's fine. And then we apply Gaussian elimination to kill tension T temporarily. And then what we find is this. Okay? Subtract. If I subtract, then this tension cancels. Instead, it becomes a capital mg subtracted by small mg. In here, it used to be negative sign. The subtract, we add these two masses. Therefore, the acceleration of x is going down. That is proportional to the gravitational acceleration. And as we have expected, because capital M is greater than small m, it is a positive number, and this is going down. Why don't we can eliminate G to find tension. Okay, the final answer is this. By the way, it's a better to write eliminate x double dot instead of G. So let me correct. I need to mark on it. Page 5. Eliminate G x double dot. Okay. Anyway, we arrived at that factor. We are now familiar with the reduced mass. The reduced mass appears always in the two-body system. And tension is now, we have tension is twice mu g. Acceleration of capital M relative to M can be expressed as this. Let's see. You know, this guy is going up, accelerates downward, and this guy accelerates upward. So the relative acceleration of these two particles are twice. That's the reason why I have factor 2. Okay. So we substitute our previous result. Y double dot minus y double dot is a plus x double dot. So it becomes this difference becomes the twice the acceleration of x. And finally, we end up with the result. If you obtain the final result, then you might want to check the change in energy, because we return to this work-kinetic-energy theorem. Amount of work done by some force resulting. If you do some work, the change, it results in the change in the kinetic energy. So if you have done some work with positive sense, your kinetic energy will increase. If you carry out a work in negative sense, then kinetic energy will decrease. If you do not work anymore, then your kinetic energy changes is 0. So kinetic energy must be invariant. Okay, this you need to check what force contribute to the work, and that results in the change in the kinetic energy. That is the next one we need to consider. After the displacement of m by delta x, speed of m changes, and we know this delta v is positive because m is here, small m is here. It's going up and it's going down. Okay. The amount of height it is falling down is the same amount of height this small m is climbing up. Before and after. After the displacement of capital M by x, you will find gravitational force applies to here, mg. What is the direction of the displacement? They are parallel, right? It's going down, and force is going down, and displacement is going down, and mg dot dx, this is a positive, parallel. So the gravitational force applies to capital M, it does work, mg delta x, that is a positive. By the way, this small m climbs up. Then the gravitational force, small mg, is going down, but this small n is climbing up. So it has a negative. So the delta y vector, and we have g, and gravitational force is applied, but displacement is upward, mg dot delta y, but this is opposite. So that is a minus mg vector dot delta x. While delta x is going down and delta y is going up, we have to replace delta y with minus delta x. We know this is a positive, but we have the negative sign. Therefore, the gravitational force applied to small m is negative. By the way, the amount of positive work, mg delta x, and the amount of negative work, mg delta x, negative. We know capital M is greater than small m. Therefore, after the displacement of capital M by delta x, the whole system experiences work done by the gravitational force in positive sense. Positive sense. On the other hand, we might want to investigate the work done by the tension. We remember this capital M and small m, we got tension. Magnitude is the same, right? And the directions are the same, right? Therefore, as a result, actually, there is something on the ceiling to sustain this pulley that applies the 2T's of force to sustain the whole system. Anyway, because this one does not contribute to the system because there is no displacement anymore, so we forget about this. However, this tension contributes to the system because there is a change in position, this displacement. The tension on the left side, T, normal direction, that is, this is E1. We have T minus E1. And another tension, this is T minus E2 or E1. They are same. By the way, force multiplied by displacement. This displacement in here is a delta x E1, downward. However, this object is going up. Therefore, delta x E1 hat minus. So we can pull this tension minus E1. This is the tension, both sides, and they are factored out, and we need to add them up. scalar product delta XE1 hat plus delta XE1 hat. They cancel exactly. Therefore, tension, these two tensions does work, but in effect, the sum of these two work done by these two tensions cancel exactly. Therefore, according to the work kinetic energy theorem, the net work done by the external force is only due to the gravitational force, and the amount of work done by the gravitational force is m minus small m g delta x. And this positive amount of work is transformed into the change in the kinetic energy, and our kinetic energy is from the whole system, 1/2 capital M plus M V squared to 1/2 capital M small m V plus delta V squared. And the difference of these two is identical to the work done by the gravitational force. Okay? The third problem. A particle of mass m is making a periodic motion on a vertical circle of radius r under gravitational acceleration. Initially, the position is here. This is a B. At this moment, its velocity is along this direction. The magnitude is this. That means it follows this track forever. Because if you go down, it becomes faster because the gravitational force does work. You know, gravitational force mg and normal force n is applied to this system. And along the circular path, normal force is always perpendicular to the track. So normal force times the displacement is always a zero. Normal force is always along this radial direction, either plus or minus, and dx, that is rd theta, e theta. So er, e theta, they are perpendicular to each other. Normal force does not work at all. Therefore, the work done by the gravitational force from here to there is mg to r. Why? The gravitational force is always downward, and the displacement, although the track is complicated, in effect, the differential, this horizontal displacement does not contribute any work because the force is perpendicular to this direction. The only direction survives, contribute to the work done by the gravitational force is only this component. Therefore, 2r is 2r e1 hat, e2 hat, minus this is the displacement, and the gravitational force is minus e2 hat mg, and multiplication. So 2 mgr minus minus becomes a plus. So this is the amount of work done by the gravitational force from B to D. Therefore, if you have a velocity v0 in here, along the direction to the left, if it arrives in here, it doesn't change the direction, so it's still rotating counterclockwise, but what you have done is the work done by the gravitational force, that is 2 mgr, on top at here, your original kinetic energy is because the speed of this particle at the initial position B was V0, work done by the gravitational force added. Finally, you arrive at the final at D point D, kinetic energy. Okay? This is based on the work-kinetic energy theorem. Okay, from this, you can determine the speed on the bottom. You multiply factor of 2, then this guy cancels, and divide both sides by r. So mv squared over r, mv0 squared over r, and you have multiplied factor of 2, it became 4mg. Okay, that force is the gravitational force and the normal force. And gravitational force, I substitute the original value, end up with at point D, it is making a uniform circular motion at this point, and we have centripetal force toward the origin, and toward the origin, this is E2 hat, E2 hat. Therefore, centripetal force is mv squared over r toward the origin. The unit minus the unit radial vector is E2 at this point. Therefore, I substitute this result came from the work kinetic energy theorem. I substitute in here. And this V0 is replaced with V0 squared. And this mg is there. This negative mg, if it moves to the right, it became plus mg. And then I need to add the 4. So I have a 5 mg on the bottom. So because it has been boosted up because of the large speed, we need a large amount of normal force in here. That's the reason why the structure should be very strong on the bottom. This factor 5, very important.